So let us start now. In this lecture, we are going to discuss about how to draw the molecular orbital diagrams for various homonuclear diatomic molecules. We have to apply the concept of molecular orbital theory. So we know that molecular orbital theory explain the formation of covalent bonds in the molecules or ions. So according to MOT, when nuclei of two atoms are close enough to each other at equilibrium distance, their atomic orbitals interact, leading to the formation of new orbitals called molecular orbitals. The atomic orbitals of the two atoms are going to interact, are going to overlap, and due to the overlapping, the new orbitals are formed. That new orbitals are called as molecular orbitals. Okay. Now there are two types of molecular orbitals are formed. One is bonding molecular orbital and other is antibonding molecular orbital. So I would like to show this with the help of this uh, diagram. You can see the overlapping of 1s atomic orbital. So 1s atomic orbital has a spherical shape. Okay, 1s atomic orbital has a spherical shape. Now, how that 1s atomic orbital get overlap with another 1s atomic orbital? You can see here in this diagram. So this is 1s atomic orbital, carry the positive sign. This is another 1s atomic orbital, carry the positive sign. And the two molecular orbitals are formed. One is bonding and another is anti-bonding. So due to the overlap between 1s, which bonding molecular orbital is formed? Sigma 1s. Okay, and anti-bonding sigma star 1s. So the bonding molecular orbital is having the lower energy level and antibonding molecular orbital is having the higher energy level. So this diagram clearly shows the overlapping of the atomic orbitals and the formation of the molecular orbitals. If two atomic orbitals get combined, two molecular orbitals can be overlapped. Okay. Now every time we cannot draw such diagrams. So better way represent the molecular orbital energy level diagram. Instead of drawing such type of the shape of the atomic orbitals. Instead of showing such overlapping between the atomic orbitals. So in the simple way now, I would like to show to you how the molecular orbital diagram can be drawn. So you can see here on the screen. Suppose that, take the example of hydrogen molecule. So I would like to draw here the MO diagram of the hydrogen molecule. Molecular orbital diagram of hydrogen molecule. Okay. So instead of showing the molecular orbitals overlapping of atomic orbitals, we have to draw here now the MO diagram, molecular orbital diagram, energy level diagram of hydrogen molecule. So first of all, we have to draw the arrow which represents the atomic orbitals and molecular orbitals are according to their increasing energy levels. So in the MO diagram, on the left side represent atomic orbitals of hydrogen. On to the right hand side, let us represent atomic orbitals of hydrogen. Okay, and the middle part, it is molecular orbitals of H2 molecule, hydrogen molecule. Now we know that hydrogen is having atomic number 1 and only one atomic orbital is there, carry only one electron. Okay, it is half filled orbital, carry only one electron. So let us represent 1s atomic orbital of the hydrogen atom on this side. Okay, by drawing such horizontal line, this is 1s atomic orbital. Similarly, the another hydrogen atom, it is having the 1s atomic orbital. Okay, so put the circle there to represent the electrons. Okay, so this hydrogen atom carry only one electron. Similarly, this carry one electron. Okay, this is having the opposite sign. Now they are going to be overlap. 1s atomic orbital of the hydrogen atom can be overlapped with 1s atomic orbital of the other hydrogen atom, and there is a formation of bonding and antibonding molecular orbital. One bonding and one antibonding molecular orbital is formed here. Okay, so this is one bonding molecular orbital and this is antibonding molecular orbital. Bonding molecular orbital is having the lower energy level and antibonding molecular orbital is having the higher energy level. Now give the designation to the molecular orbital. As this molecular orbital is formed by due to the overlapping between 1s atomic orbital, so it will give sigma 1s bonding molecular orbital. So give the designation to this molecular orbital sigma 1s and antibonding molecular orbital sigma star 1s. So we have to write here sigma star 1s antibonding molecular orbital, where the bonding molecular orbital is having the lower energy level and antibonding molecular orbital is having the higher energy level. So in this way, the two 1s atomic orbital which are having the same energy and same symmetry can be overlap, can be interact, and they will give rise to two molecular orbitals. One is the bonding molecular orbital and another is the antibonding molecular orbital. Now, there are two half-filled orbitals, two unpaired electrons. So these two electrons goes to the lower bonding molecular orbital. Okay. Now there are no electrons are here. So antibonding molecular orbital is empty. So this is the molecular orbital energy level diagram of hydrogen molecule. Once we draw the MO diagram of the molecule, then we can calculate the bond order in the hydrogen molecule. Okay, means we want to know how many number of the bonds are there in the hydrogen molecule. So let us see here the bond order of the hydrogen molecule. It is equal to, so there is a formula which is given to calculate the bond order. So that formula is that number of bonding electrons minus number of antibonding electrons divided by 2. Now you have to see this diagram, and in this diagram you have to tell me how many number of the bonding electrons are there. Those electrons which are present in the bonding molecular orbitals, they are called as bonding electrons, and those electrons which are present in the antibonding molecular orbitals, they are called as antibonding electrons. So we can now uh, calculate the bond order here. Number of bonding electrons are only 2. Number of antibonding electrons, no electrons are here, 0 divided by 2. So it is equal to 1. It means that bond order in the hydrogen molecule is 1. So therefore, in hydrogen molecule, there is a single covalent bond, and that covalent bond, it is a sigma bond. Okay, that covalent bond, it is a sigma bond because there is a formation of sigma molecular orbitals. Okay, due to the overlapping between two 1s atomic orbital, we have to show this overlapping of the 1s atomic orbital. Okay, the 1s atomic orbitals are at the line joining the internuclear axis. Okay, so it will give two molecular orbitals. One is the bonding molecular orbital which is having the lower energy, and other is the antibonding molecular orbital which is having the higher energy. So this is sigma bonding molecular orbital. Okay, so this is the MO diagram of the hydrogen molecule. Now on the basis of the MO diagram we can explain three things. First, it is bond order. We can calculate the number of the bonds in the molecule, that is bond order. Second, we can write the electronic configuration of the molecule. We can write the electronic configuration of the molecule. Just we know the atom is having the electronic configuration, the molecule is also having the electronic configuration. And third thing, that is magnetic behavior. Okay, on the basis of the valence bond theory, generally magnetic behavior cannot be explained, but this molecular orbital theory explain the magnetic behavior of the molecule. Okay, so bond order, it is one there, single covalent bond between the two hydrogen atoms. Now what is about the electronic configuration? So you can see there is only one bonding molecular orbital, that is sigma 1s. So we can write the electronic configuration of the hydrogen molecule in this way. Okay, so you can see here hydrogen 1s1 atomic. Similarly, another hydrogen atom, it is having 1s1 electronic configuration. It will give H2 molecule. So H2 molecule, it is having now this sigma 1s bonding molecular orbital. How many number of the electrons carry? 2. So sigma 1s2. This is the electronic configuration of the hydrogen molecule, sigma 1s2. There are no electrons into the antibonding molecular orbital, so not necessary to write here the antibonding molecular orbital. So this is the explanation of the electronic configuration. Now let us going to explain the magnetic behavior of the hydrogen molecule. What is about the magnetic behavior of the hydrogen molecule here? So you can see the hemodiagram for this purpose. In the bonding molecular orbital sigma 1s, all the electrons are paired. No one electron is unpaired there. So if the molecule is having all the electrons are paired, then the molecule is dimagnetic. And if the molecule is having one of the unpaired electron, then it is paramagnetic. But hydrogen molecule is having all the electrons are paired, therefore it is dimagnetic. So hydrogen molecule, it is dimagnetic. It is having the dimagnetic behavior. It is having the dimagnetic behavior. So on the basis of the hemodiagram, we can explain the three important things: bond order, very important, electronic configuration, as well as magnetic behavior of the molecule. So this is the hemodiagram of the hydrogen molecule. Okay, so instead of drawing such shapes, because it is quite difficult to draw such shapes of the molecular orbitals. Okay, so that is not correct thing. Therefore we have to draw the molecular orbital diagram of the hydrogen molecule or any molecule. This is the first example. Now let us going to draw the another molecule, hemodiagram of the another molecule. So take the another molecule here after the hydrogen, that is helium molecule. Second molecule, now I would like to draw the diagram of the hemodiagram of the helium molecule. So you have to just watch here, because now I am recording the video here. So hemodiagram of helium molecule. Okay. So let us write first of all the electronic configuration of the helium having atomic number 2, 1s2. Okay. So draw here the vertical line to represent the atomic orbitals and molecular orbitals are arranged according to the increasing energy level. On to the left hand side, let us write atomic orbitals of helium. On to the right hand side, let us write atomic orbitals of helium atom. And middle side, it is the molecular orbitals of helium molecule. Okay. See, there is only one atomic orbital, 1s. So represent here 1s atomic orbital of this helium atom. Similarly here 1s atomic orbital which are having the same energy level, same symmetry. And on the basis of the molecular orbital theory, we know that the two overlapping atomic orbitals must have the same symmetry and must have the same energy. Then and then they can be overlap and they will give the molecular orbitals where there is a formation of one bonding molecular orbital and another it is an anti-bonding molecular orbital. Now here put the circle in the 1s atomic orbital to represent the electron. Similarly here, now there are two electrons here, so put the two electrons here. Okay, now these two atomic orbitals get overlap. So 1s overlap gives one bonding molecular orbital, that is sigma 1s, and anti-bonding molecular orbital, that is sigma star 1s. Okay, sigma star 1s anti-bonding molecular orbital, it is formed here. So put the circle for representing the electron. Now there are 2 plus 2, 4 electrons in the molecule. Okay, so the first two electrons goes into the bonding molecular orbital. and remaining 2 electrons now goes into the antibonding molecular orbital. Okay. So bonding molecular orbital is having 2 electrons, antibonding molecular orbital is having 2 electrons. Okay. So on the basis of this MO diagram, now this is the MO diagram of the helium molecule. So we can calculate first bond order. Okay. On the basis of the MO diagram, we can calculate the bond order. It is equal to number of bonding electrons minus number of antibonding electrons divided by 2. So it is equal to bonding electrons are 2, antibonding electrons are 2, divided by 2. So 2 minus 2 0. So it is equal to 0. Bond order is 0. It means that helium molecule does not exist. Bond order 0 indicates that there is a no bond between the two helium atoms. There is a no bond between the two helium atoms. Okay. No bonding is there. Bond order is 0. So no need to write the remaining part, that is electronic configuration and magnetic behavior. As there is a no bond, helium molecule does not exist. Helium molecule does not exist as there is a no bond. Okay. So we can explain on the basis of the molecular orbital theory. The same has been already explained on the basis of the valence bond theory also. Okay. Now this is the second molecule, helium molecule. Now let us going to be draw the next molecule now here, that is after helium. I would like to draw here the next molecule, its MO diagram. Third molecule now here, lithium molecule, Li2 molecule, the MO diagram of lithium molecule. Okay. So lithium, atomic number 3. It is having the electronic configuration 1s2, 2s1. Okay. Now this is the outermost cell. Only one electron is there. This is inner cell. So only valence electrons are participate into the bonding. So the MO diagram will be like this. Its MO diagram you can see. Now you are going to appear for objective type of the examination, so no need to draw the diagram. Okay. But we can calculate the bond order, magnetic behavior, and electronic configuration of the molecule. So let us write here atomic orbitals of lithium atom. Okay. Same here, atomic orbitals of lithium onto the right hand side, lithium atom, and middle part it is molecular orbitals of Li2 molecule. So see here 1s atomic orbital of lithium and 1s atomic orbital of lithium. Now let us represent 2s, which is having the higher energy. This is 2s. Similarly here 2s atomic orbital of the lithium. Now as this 1s atomic orbital, it is not the part of the valence shell. Therefore, it is not involved into the bonding. We know that in the bonding only the valence electrons are participated. Only the outermost electrons are participated. So there is a no bonding between this 1s. Okay. First of all, put the electrons into the 1s atomic orbital and 2s atomic orbital. So 2 electrons are here, 1 electron is here. Similarly on this side, 2 electrons are here, 1 electron is here. So as 1s it is not the part of the valence shell, we just have to be write there no bonding. No bonding is there because it is not belongs to the valence shell. But we have to represent in the MO diagram. Next, now this is 2s orbital, it is belongs to the valence shell. So it can be involved into the bond formation. So 2s atomic orbital get overlap with 2s atomic orbital. Okay. And there is a formation of one bonding molecular orbital and one anti-bonding molecular orbital. One bonding and one anti-bonding molecular orbital. So which bonding molecular orbital is formed here? Due to the overlap between 2s and 2s. So 2s can overlap with 2s. It will give two molecular orbital. One it is sigma 2s bonding molecular orbital and other it is sigma star 2s antibonding molecular orbital. So give the designation to this bonding molecular orbital sigma 2s and sigma star 2s, antibonding molecular orbital. Now put the circles here to represent the electrons into the bonding and antibonding molecular orbitals. Now there are only two electrons here, 1 plus 1. So that two electrons will be goes to in the bonding molecular orbitals, and antibonding molecular orbital, it is totally empty. So this is the MO diagram of the lithium molecule, Li2 molecule. So on the basis of this MO diagram, first of all, we have to explain now the bond order. Okay, number of bonding electrons minus number of antibonding electrons divided by 2. So you can see in the MO diagram, sigma 2s bonding molecular orbital is having 2 electron. So 2 bonding electrons are there. Antibonding, no electron here, 2 minus 0 divided by 2. So it is equal to 1. So bond order in the lithium molecule, it is 1. That is, there is a single covalent bond between the two lithium atoms. Sigma bond between the two lithium atoms in the molecule. Second, now electronic configuration of the lithium molecule. Now in this case, to write the electronic configuration, it is more important. How to write now? So let us write here Li2 molecule, Li2, electronic configuration of the lithium molecule. Okay. See here, even though these electrons are not participate into the bonding, 1s, 1s, but in the electronic configuration, we have to represent that atomic orbitals. Just like in the atom, we represent the electronic configuration 1s2, 2s1. For lithium atom, the same will be here for the molecule. Okay, so for the molecule also we write the electronic configuration of the lithium molecule. So 1s atomic orbital and this 1s atomic orbital. So we cannot directly write here 1s 1s, but we can put the another symbol. Instead of writing 1s, I would like to write here K for 1s. K means 1s2. K means first cell. Okay, K is the first cell from the nucleus. This is the K cell which carry 2 electrons. Okay, and that 2 electrons will be here in the 1s orbital. Okay, this is one first cell and having the 2 electrons, K cell. So K for this 1s, similarly K for this 1s. Then write next orbital, next bonding molecular orbital, according to the increasing energy level, that is sigma 2s. It is having 2 electrons. Okay, it is having 2 electrons. So put here the 2 electrons, sigma 2s. It is having 2 electrons here, sigma 2s2. That is the electronic configuration. So lithium molecule is having Kk and sigma 2s2. That is the electronic configuration of the lithium molecule. This is second part. Now third part, it is the magnetic behavior of the molecule. Why we are drawing the MO diagram here? Because we want to explain the 3 important things. First one, it is bond order. Second one, it is electronic configuration of the molecule, and third one, it is the magnetic behavior. As the diagram shows that all the electrons are paired, no one electron is unpaired here. So lithium molecule, it is dimagnetic molecule. No one electron is unpaired there. All the electrons are paired. These 2 electrons are paired. Everywhere there is a paired electrons. So lithium molecule, it is a dimagnetic molecule. So in this way, we draw here the MO diagram of the lithium molecule. Okay. So I think you know how to draw the MO diagram of the lithium molecule. Now let us try for the next molecule, that is beryllium molecule. Let us go to draw the molecular orbital diagram of the beryllium molecule. This is the 4th molecule. Okay. Let us revise first the molecular orbital diagrams we have been drawn here. First, it is hydrogen molecule. Okay. Then second, it is helium molecule. Then third, it is lithium molecule. Now, the bond order in the hydrogen molecule is it is 1 here. Okay. Then helium molecule, it is 0 here. Lithium molecule, once again it is 1. Hydrogen molecule, magnetic behavior. Its magnetic behavior, it is dimagnetic because all the electrons are paired there. In case of helium molecule, no need to explain because it is not a molecule. Lithium molecule, it is also diamagnetic. Okay. Now electronic configuration of the hydrogen molecule. Electronic configuration of the hydrogen molecule. So hydrogen molecule is having the electronic configuration. It is sigma 1s2. 2 electrons are there. For helium molecule, not necessary to show the electronic configuration. And for lithium molecule, the electronic configuration, it is K, then sigma 2s2. That is the electronic configuration of the lithium molecule. Now let us going to draw here the MO diagram of the fourth molecule, that is beryllium molecule. Beryllium molecule. Okay. So beryllium, atomic number 4, electronic configuration 1s2, 2s2, 2p0. 1s2, 2s2. Okay. No electrons into the 2p orbital. So there are 4 electrons, but out of 4 electrons, 2 are into the inner shell and 2 are into the valence shell. So let us draw here the atomic molecular orbital diagram of the beryllium molecule. So the atomic orbitals and molecular orbitals are according to the increasing energy level. So right here, atomic orbitals of the beryllium atom. Atomic orbitals of beryllium atom here onto the right side, left side. Then atomic orbitals of what? Beryllium atom. And middle part, it is molecular orbitals. Molecular orbitals of beryllium molecule. Okay, beryllium molecule. So 1s, 2s. Let us represent 1s here, having lower energy. Similarly, 1s atomic orbital. Okay. Then 2s having higher energy. So this is 2s atomic orbital. Put the circles there to represent the electrons. Now 1s is having 2 electrons, so represent 2 electrons here. 2s is also having 2 electrons, so represent 2 electrons here. Same on this side, 1s2, 2s2. Okay. Now you can see here this 1s, 1s, there is a no bonding as it is not the part of the valence shell. No bonding is there. Okay. Now 2s atomic orbital of the one beryllium atom get overlap with 2s atomic orbital of the another beryllium atom. And there is a formation of one bonding and one anti-bonding molecular orbital. One bonding and one anti-bonding molecular orbital. So we can represent one bonding and one anti-bonding molecular orbital, that is sigma 2s bonding molecular orbital and sigma star 2s anti-bonding molecular orbital. Okay. So put the circle there in the bonding, one bonding and one anti-bonding. Now there are 2 plus 2, 4 electrons in the beryllium molecule. Okay. So we can represent now the 4 electrons here. 2 will be goes into the bonding molecular orbital and 2 will be goes into the anti-bonding molecular orbital. So on the basis of the MO diagram, now we want to calculate the bond order here. Okay. So bond order, it is equal to number of bonding electrons minus number of anti-bonding electrons divided by 2. So number of bonding electrons we cannot count these bonding, these are not the bonding electrons as there is a no bonding. These two bonding electrons, antibonding 2, this divided by 2, so it is equal to 0. So as there is a no bond order, no bond between the two beryllium atoms, so beryllium atom does not exist. On the basis of the molecular orbital theory, beryllium molecule does not exist. Beryllium molecule does not exist as there is a no bond order. So try to understand about this. There is a bond order becomes equal to 0. So no bond order is there. It means that molecule does not exist. So no need to write the electronic configuration of the molecule, and no need to write the no need to explain the magnetic behavior of the molecule. So this is the molecular orbital diagram for beryllium molecule. Okay, so up to this now it becomes very simple. Now I would like to draw the next molecule here, the molecular orbital diagram of the next molecule. So before going to draw the molecular orbital diagram for the next molecule, I would like to show what type of the molecular orbitals are formed there. Okay, in the molecule. First of all, we know that when 1s atomic orbital get overlap with 1s, two molecular orbitals are formed, that is sigma 1s and sigma star 1s. Okay, we can show this in this way also. This is 1s, this is 1s, forms two molecular orbitals. One is bonding molecular orbital and another is antibonding molecular orbital. Okay, antibonding molecular orbital. So it can be shown in this way. Okay, one bonding, one antibonding. So this is sigma 1s bonding molecular orbital, and this is sigma star 1s antibonding molecular orbital due to the overlap between 1s 1s. Similarly, when 2s get overlap with 2s, the same bonding molecular orbital and antibonding will be formed. So sigma 2s now. All these are sigma bonding molecular orbitals. Because s orbital, it is suitable to formation of the sigma bond. So sigma 2s and sigma star 2s. Now let us take 2p orbital. Now there are three 2p orbitals. First of all, it is 2px, then 2py, then 2pz. Three orbitals are there. Actually, all the p orbitals are having the same energy level. But when the 2px atomic orbital of one atom get overlap with 2px or atomic orbital of the another atom, there is a formation of two molecular orbital. But that two molecular orbitals are not sigma molecular orbitals. That two molecular orbitals are not sigma molecular orbitals, because the 2px atomic orbital, it is not suitable for the formation of the sigma bond, which gives pi 2px, pi bonding molecular orbital, and pi star 2px, antibonding molecular orbital. Okay, let us show this bonding molecular orbital. So 2px atomic orbital, this is 2px, suppose, then another 2px. Okay, so this overlap gives pi bonding molecular orbital, because lateral overlap is there, sidewise overlap is there. The lobes of the atomic orbitals are perpendicular to the internuclear axis. So they are not giving the sigma bonding molecular orbital here. You can see here, due to the overlap between 1s, 1s, the lobes of the atomic orbitals are onto the line joining the internuclear axis. Frontal overlap is there. Head-on collision is there. So it will give sigma bonding molecular orbital. Okay, and 2px atomic orbital of one atom when overlap with 2px atomic orbital of the other atomic orbital, it will give pi bonding molecular orbital, pi bonding and pi anti-bonding. So bonding will be formed in this way. So bonding molecular orbital, it is having the, so bonding molecular orbital can be shown in this way. Okay. So the bonding molecular orbital can be represented in this way. Okay. Combination of the atomic orbitals here, similarly here. Okay. Positive, positive overlap, negative, negative overlap. So this is pi to px. And pi star to px can be represented now in this way. Okay. Pi star to px. The lobes of the atomic orbitals are not going to be overlap with each other. Okay. Positive, negative overlap get cancelled there. They are away from each other. In case of pi star to px atomic antibonding molecular orbital. So this is pi star to px. So in this way, 2px gives pi to px, pi star to px. Similarly, 2py gives by the same way pi to py, pi star to py. Same pi bonding molecular orbitals are formed there. But 2pz gives sigma bonding molecular orbitals, that is sigma 2pz and sigma star 2pz. So you can see how there is a formation of the sigma 2pz bonding molecular orbital. So let us take here 2pz atomic orbital. This is 2pz. The lobes are lies along the internuclear axis. This is suppose z axis. This is x axis and this is y axis. Okay. Another 2pz orbital. Okay. It can be overlap. Okay. So we can show this positive overlap. The lobes are lies along the internuclear axis. So it will gives pi bonding molecular orbital. A sigma bonding molecular orbital. Sigma bonding molecular orbital and anti-bonding molecular orbital. So remember, in the 3p orbitals, the 2p orbitals are involved into the pi bonding molecular orbital, and 1p orbital, that is pz orbital, it is involved into the sigma bonding molecular orbital. So this is most important here, how there is a formation of the sigma bonding molecular orbital and there is a formation of the pi bonding molecular orbital. There are two types of the molecular orbitals, sigma bonding molecular orbital and pi bonding molecular orbital. So sigma bonding molecular orbitals are formed by the atomic orbitals which are lies along the internuclear axis, their lobes lies along the internuclear axis. And pi bonding molecular orbitals are formed by the atomic orbitals which are perpendicular to the internuclear axis. The lobes of the atomic orbitals which are perpendicular to the internuclear axis. So it will give pi bonding molecular orbitals. So thus now in this lecture we explain the two molecular orbitals. Okay, sigma bonding molecular orbitals and pi bonding molecular orbitals.